We will make this really quick. We should be able to fit it. So what I'm going to do is first simulate a series. I'll call my observed series as X. Length 256 and the AR part, since we're using R, I'm going to put a negative coefficient, so minus 0.64. The MA part, minus 0.32. That is my series, yes. In R, you can make a fit pretty easily. It's just a ring. And you put in the series that you have, and you have to specify the order. You might wonder, well, how do I know the order? Well, that's why we have model identification. Model identification is going to tell me what order to use. Since I started with ARMA 1.1, I'm going to go with that. But do keep in mind, just because I simulated an ARMA 1.1 doesn't mean the best model is ARMA 1.1, because this is a simulated series. And we typically say include mean equals false, because we subtract the mean out. Of course, we can add it right back in at the end. Okay. So I'll just do this. So if you look at, just type in fit.physics, you get a bunch of values here. It tells you the coefficient for AR is estimated to be negative 0.7304. MA1 is negative 0.1806. These are varying, they have variability, we are estimating. So we need to have SE. From Statistics 2023, what is SE? Standard error. Do the same thing, plus or minus 2 standard deviations to get a range of values, to get a hint. You can look at sigma squared here. It is estimating it to be 1. Do we recall as to why? It will be close to 1. What type of noise do we typically use? White noise. White noise is simply standard normal, mean 0, standard deviation 1, so the variance usually close to 1. The other items here, log likelihood, AIC, those are used to see if a better model can be used. For instance, instead of an ARMA 1.1, let's say I simply do AR. that's what I get. The AIC here is 737.39. Previous case, AIC is 733.86. The lower the AIC, the better your model. So the AR1 model has higher AIC than the ARMA 11. So the reasonable model is ARMA 11. But okay, I can do this. What I'm going to do now is to come up with the fit. There are packages which will give you a fitted series, or I don't know which ones are available because our updated a bunch of stuff. So what I'm going to do is for the fitted series, I'll call it X hat. I have to start X hat somewhere, right? So I'm going to start it at the first observation, and I have to start the noise somewhere. So I'm going to start it at 0. Now I'm going to fit the values, so starting at 2, all the way up to the length of the original series, -1. So xt would equal to phi times xt minus 1 plus theta times epsilon t minus 1 plus epsilon c. So to get the fitted values, the next step would be k plus 1. So I'm going to get the value of x2. It will be based on x1, previous value. Negative 0.73 and negative 0.18. So negative 0.73 times previous value of x. So x okay. Mind you, I'm using the observed value that is in the data because I'm not forecasting. I'm just fitting the actual data that I have. So mine is 0.18 with an n8 part. So 0.18 minus multiplied by epsilon. But at each step, I've got to evaluate my residual. So the residual at step k plus 1 would simply be the actual value, which is x, minus the fitted value, x hat. Good, actual minus fitted. Observed series. What have I got from the model? So I already have the observed series in black. Let's see what this one looks like. Color 2. So the dotted lines would represent the actual series. The fitted values are in red. Okay. Is the model performing okay? Well, it's reasonably doing well, but there are places where the prediction is not that great. Now, how can we improve this? Observing it over a longer period of time. Good. We pretty much did what we needed to do. Any questions?